to the course TP 4165, Computation of Heat and Fluid Flow. Last time we started looking at the finite volume method, and to remind you, I would like to have a short look at the lecture notes. What we have been assuming is 1D flow, 1D heat conduction. So we assume now that we have three control volumes that we see here. We just look at x direction, here is the temperature, and here we have our control volume omega p, just the part that is on the x-axis. Remember, in the cross-flow direction we have a constant cross-section. And then we have two neighbors, west and east, and we found out that we can write the heat equation, in that case, exactly in the form where the where the average of the temperature is involved. Let's see if that. Yeah. So this is this form. So in here we have the time derivative of the average temperature in cell omega p. That is defined here. So we have we take the integral over the exact temperature from the western phase to the eastern phase, from xw to xe, and divide by the distance of this interval. And then we can formulate this. What we see is, when we just work with cell averages, we need to compute these derivatives, actually with the alpha, with the thermal diffusivity in front, at the eastern and western phases. And that is a problem because we only know the averages. But what we started arguing is that we can use the neighboring values, and then we can use the difference between the values of the averages at the midpoints. So we locate the averages at the midpoint of the cells. For example, here at P, that's the midpoint between XW and XE, and there we locate the average. And likewise in the eastern and in the western cells. And then we can take the derivatives by, as we do in finite difference method, by approximating the derivatives by finite differences. So that's the idea. So let us then write that, what we do here. So we approximate then the derivatives, and we focus on the eastern phase. We can also write for the western phase. First we do at the eastern phase. So we want to write that at the eastern phase. And we approximate it by taking the approximation of the cell average in E minus the cell average in P divided by the distance between them. And then we have an approximation of the slope. So that is then TE minus TP. And the notation is that now the capital T with the underscore are then the cell averages in the respective cells. Divided by the distance, that is then the x location of the cell average of the midpoint in cell E minus the midpoint of cell P. So that is quite an obvious approximation, which is then motivated by the finite difference method. But we make an assumption that we can approximate the nodal values at the midpoints by the cell averages. We do an analysis of that, we find out that is true to second order. So second order means the error is of the order delta x squared. Likewise, we can do it at the western phase, so that we have an approximation of the derivative at the western phase, so that is a little w, and then we take, similarly as we did for the eastern phase, we take the values that we have in P and W, and approximate by that the derivative. So then we get, in that case, we get Tp minus Tw, that is now capital W. So the capital ones are the averages in the cell, and the small ones are the values at the faces. Again, divided by the difference, by the distance between the midpoint in cell P and the midpoint in cell W. So that is then what we can do to approximate the derivatives at the faces. So that is, everything is then clear. What we also need to do is to approximate the thermal diffusivity, alpha. If alpha is constant, or if it's a value given as a function of x, we know it also at the faces. But if alpha is nonlinear, that is when alpha is dependent on T, on the temperature, we need also an approximation on that. So there we have essentially two options. That is the first option, if we want to approximate the thermal diffusivity at the phase E, what can we do? Well, the obvious one is to take the arithmetic average. So it is to take the average then of the value that we have in the cell P and the value that we have in the cell E. So that is the, you can say, the arithmetic mean. Likewise, we can do that also at the western phase, similarly. But we have another option, and this other option is useful when these values differ largely. So when there is a jump, essentially, in the thermal diffusivity, then another option is better, and that is the following one. Then we get the alpha E approximated as what is called the harmonic mean, and that is 2 alpha P times alpha E divided by alpha P plus alpha E. So that is the harmonic mean. So where can we use either of them? First one we can use when they don't differ that much. So that is, say, for alpha P, when it's approximately equal to alpha E, so when they don't differ very much. And the harmonic mean is for alpha P much larger than alpha E or much smaller. You can also use it for the case when they don't differ very much, but when they don't differ very much, you will find by an analysis that you end up with the harmonic mean. But the point is that the harmonic mean is useful when the values differ largely. What we mean here by this notation is that we assume here the alpha P to be a function of Tp, and so on. So we assume that the values then are nonlinear and dependent on the temperature. And that is then dependent on the temperature at the point where we are, or in the cell where we are, and so on. Okay, so now we do the similar thing then for the western phase, and then we get into the approximation that we have been looking at. So we insert now these approximations that we have made to the derivatives and also to the thermal diffusivities in this equation. So and then we use now the approximations, because at this point here, what we do here, this and this, these are all approximations. Then we are no longer exact. This equation with the exact temperature is exact. But when we go here, we make approximations. And then we get the finite volume method. There we do approximations of the cell averages. So now let us do that. get. That is the 4 and either 5A or 5B. So we decide whether we use harmonic mean or arithmetic mean or harmonic mean. We insert that in equation. We use these approximations, then in the equation 3, that is the one that has here the number 3.6 that we just discussed. Then the finite volume method for the heat equation in 1D becomes, so that was what we looked at last time, the 1D heat equation. That is then the following. First, we have seen already that that is what we hope to have already on the equation 3 or 3.6, that we approximate the exact cell average by the finite volume approximation. So therefore, the hat that we used for the average is gone. So now this is an approximation to the cell average of the temperature in cell P. On the right-hand side, we use now these approximations, and we don't specify whether we use this or this, but we just write the alpha E. We know that it will be, in the general case, depend on the temperature in the neighboring cells. What we write is the difference that was for the cell, for phase E, it was TP minus TE minus TP divided by the distance between the midpoints, and minus, then we have the same thing at the western phase. So that is then our finite volume approximation that we get for the 1D heat equation. And what we use here all the time now, that we should remember, is that the TP that is appearing here is the approximation to the cell average, but it's still time dependent. So we are continuous still in time. So that is dependent on T. It's dependent on the temperature and so on. So that means also the similar applies for TE and for TW. And this is called a semi-discretization, because we have discretized in space, but not yet in time. So time is still continuous. You see, we have still here a nice derivative. So we have to discuss how to do that later. But it makes sense first to do the approach that we also did in last course, Introduction to CFD last term, when we discussed the finite difference method. There we did the approximation using the differential form of the equations, made finite difference approximations, and we ended up with something similar. It's not exactly the same, as we shall see in a minute. Now we have focused just on one cell. Now we want to look at the whole picture and solve the problem where we are in, where we want to solve the heat conduction problem like we do now in exercise 1, for the heat conduction in a rod, for example. Then we have not just one cell, but we have a couple of cells. In the example that you will look up then for exercise 2, that will come on Friday, you will look up at a rod which we divide into 100 control volumes. Then we have to compute then the temperature there. So how do we do that? So first of all, we want to say what we want to do. So we want to solve the heat equation interval that we say is called XA, XB. So that will be the end faces, the exponents of the end faces of this rod. And we want to do that. It will also be done like we already do now for the exact solution in exercise 1. We will do that similarly for the numerical solution. We will use so-called Dirichlet boundary conditions. For the boundary conditions, I frequently use the acronym BC, so when you see that. But the term that you have seen already, those who followed the course, the last term, that is when we discuss boundary conditions. We have two types that we mainly discuss. Dirichlet boundary conditions, where we give the values of the unknown, or Neumann boundary conditions, where we give the derivative of the unknowns. So here we have Dirichlet boundary conditions, and that means that the boundary condition at the left end of the domain, XA, with time, is given as a function of time. So this is given. In our case, it will be constant, it will be minus 100 degrees Celsius. And at the right end of the domain XB, we have then similarly given a boundary condition, which can also be like left time dependent, but in our case, for example, for exercise 1, this is a constant, it is 500 degrees Celsius in our example. And what else do we have? We have an initial condition. So we have a boundary conditions at the left and right, and the domain, and we have an initial condition. There, I frequently use the acronym IC for initial condition. And the initial condition means that we have given that the value of the temperature in the domain at the time t equals 0 is equal to some given function. I call it t0 of x. The example of the exercise 1, it's simply the temperature is in the beginning 0, except for the boundary values. There they are imposed at time equal to 0. So that is frequent that we observe problems in computational fluid dynamics, which can be characterized as initial boundary value problems. We have an initial condition at time t equals 0, and we have boundary conditions, and we have to solve the partial differential equation, the PDE that governs the flow that we want to solve, or the heat conduction problem in this case. So, how do we proceed then? Well, we divide our domain into a number of cells. So, let's do that. I'll also do that already here in the lecture notes. Let's see, here it is. So, we divide the interval, which is in our case our domain, that is given by the interval xb into what is now just a convention that we call it nj, number of control volumes. Cells for that. And and then these intervals look, or these control volume cells in 1D, they will just be intervals that are xj minus 1/2 to xj plus 1/2. And we let j go from 1 to nj. the example that we'll have then in exercise 2, the nj will be 100. We have 100 control volumes of cells. You see the name is a little bit strange to have cell volumes for 1D, but it's just a convention. Use the same name if we have intervals, or if we have surfaces or volumes in 2 or 3D. So what does it look like? So we have our interval. X here. And this is the temperature. Here we have XA, that is the left boundary. And here we have XB, which is the right boundary. And then we have NJ cells. That is some examples. So here, they don't need to be equidistant, they can be whatever you like. So that's, by the way, a strength of the finite volume method that we have already here some geometric flexibility. So then we say we locate the midpoints of each cell. So that would be the first cell, that would be midpoint in the first cell x1, and so on. And we shall focus for the discussion to some control volume that is away from the boundaries, and there we call the midpoint xj, or if we use the notation that we used before, would be p, and the western neighbor would be the midpoint in the western neighboring cell, that is the w, would be xj minus 1. Then we have also the midpoint in the eastern neighbor, that would be then the xj plus 1. And the faces of the cell, that is the cell j in that case, these ones here, they are denoted by xj minus 1/2 and by xj plus 1/2. So you see the reason for that is simply that the faces are between the cells, and then they get a half index. So that makes the notation then in a way obvious, so that you call that in the other notation that we have been using was called this little w and this little e. So that is then we use both notations with letters for the central cell P, neighboring cell E and W, east and west, and then for the indices we do it in this way. So then we have then a clear distinction between the midpoints, which have full index, and the half indices are then indicating the faces. Okay, so now we apply we want to discuss a little bit more first here. What is given? Remember, we have the boundary temperatures given by the Dirichlet conditions. So in our case, say we have some temperature called TA. That is given. We don't need to compute that. And we have given the temperature that is at the right boundary, which is TB. So we have also here temperature. And then what we have to do, we have to compute the cell averages inside for all control values. And we have to do that for each time step. So at the moment we have not yet done the time stepping, but that will be later on the goal, to compute at each time step the temperatures in all cells. So we could imagine that we have, say, a value here, Tp, and remember that is then dependent on a certain time instant. We have the value, say, Te here, and say we have Tw, and we use the same time, we use the notation that this is equal to Tj or Tj plus 1, and that is the capital W, that is the tj minus 1. So we use this notation. So imagine we have, what we have to do in the end, we have to compute the temperatures in all cells. Okay, to do that, we apply the approximation that we have just derived previously, and now we don't write it for the cell omega p, we write it now for the cell j, for the cell number j. So we use now the index notation instead. That makes it easier to distinguish. So then, we apply what we had derived before. I call it now the semi-discrete form of the finite volume method to each control volume. However, for two exceptions, except for the first and last ones. That will become obvious when we look at it now. So, instead of delta xp, we use now delta xj. Of course, then we use the indices and we can more easily identify each one. So that's the delta xj is the distance of the cell j. So that is xj plus 1/2 minus xj minus 1/2. So this distance here, that is the delta xj. So, and then we have the time derivative of the temperature in cell J, that is the average temperature in cell J. And on the right-hand side, we have then the term of diffusivity. We use again, instead of the east, we use the J plus 1/2, the half index, which is then located here. It was E before, now we use this. And then times the approximation of the derivative. Now we use, of course, then these indices here, tj plus 1 minus tj, to get an approximation of the slope at the eastern face. Here at the western, we will use a similar thing. We will use then this difference approximation to get the slope here. So that gives them the following. We get the tj plus 1 minus the tj divided by the distance between the respective midpoints minus alpha j minus 1/2, that is what was western before, times the difference approximation that we have at the western face now, which is then tj minus 1 divided by the distance of those midpoints. So we use then this to approximate the slope at xj minus 1/2. So that is then what we do. And now we can look where we can use it and where we cannot use it. You see, what we have been discussing here was a cell in the interior. There we have a western neighbor and an eastern neighbor. Or if we have this notation with the indices, cell J, we have the neighbor J plus 1 and the neighbor J minus 1. But when we are in the first cell, we don't have a left neighbor. So we cannot use this here to do this approximation here. We don't have, and when we are here at want to have an approximation in the cell 1, we would need T1 minus T0. T0 is not given, so we have to do something else here. So that is one limitation, and the other limitation is when we are in the last cell. We have not given a name for that, we argue we have nj cells, so that means the midpoint of the last cell will be x nj. So there we cannot do it either, because we don't have the value tnj plus 1. This is simply not given. So it means the limitations are then, we can do everything, everywhere, except for the first and last control volumes. So therefore we will now introduce some, we'll look at how we do it there. Let's see, we will call this here. We'll call this here, let's see, I call this number B. And I call this one here number A. So we will have to do a different approximation for the first cell to number A. Should be here. So that means for the first cell, let's see, that gives me difficulty here with the space on the blackboard. Let's see, maybe we can take it off in the interior. Just focus on the boundaries. So, in first cell, so we approximate our expression A for the flux of the temperature. That will be for J equal to 1 by the following. That will be then, I call it then the A. And that will be, let us discuss that. What do we need to approximate? We need to approximate alpha dt dx. And we need to approximate it at the left boundary itself. Right? Because we are discussing this cell here, and what we previously called the western boundary is actually at the boundary of the domain itself. So that's in a way good, because then we can take the value that we have, TA, to compute the thermal diffusivity alpha. So that we have exact by that. So that is not a problem. But what is the problem? Well, we have also a cell average. Let's see, we assume we have a cell average here. So this is our T1. We need to approximate our derivative. And how can we do that? We simply use the value in the cell 1 and the boundary value to get an approximation of the derivative. So that means we shall use now T1 minus the temperature at the left boundary TA divided by the distance between the midpoint of cell 1 and the left boundary of the domain XA. So then we have an approximation. So that is then what we shall use in the first cell instead of this expression which we cannot use because we don't have the left domain there. For the last cell, we shall do something similar. So in the last cell, that is in our case then the cell Nj, we approximate then B, again we approximate alpha dt dx there. That will be then for J equal to Nj by the following. Will be then we call it Z. What shall we do there? Well, the alpha is again nice. We know we are at the boundary. We want to compute alpha dt dx at the boundary, the right boundary. We have Tb, so we can compute the alpha there. The alpha B is then the alpha of Tb. So that is exact, no problem. The derivative, we do a similar thing as we discussed for the first cell. We use the value Tnj and the boundary value. And the derivative approximation is then using the difference approximation TB minus TNJ divided by the right boundary location XB minus the midpoint in the cell NJ. So then we use this in the last cell. And then we have discussed everything. And what we have on the left, the general case, we can now also give the J. We have not yet given that. That is then for J equal to, where can you start? You can start from 2, because there we have neighbors, the left neighbor, and so on. We can go to Nj minus 1. So those will be the indices for which this approximation is valid. For cell J, we have to use this approximation instead of this. This can still be used, because for J equal to 1, we have here T2 minus T1. Both are given, no problem. T2 and T1 are given. So likewise at the right boundary, we can still use our approximation at Nj minus 1 off. That is, this approximation can still be used because we have then Nj and Nj minus 1. That is given, no problem. What we have to do at the last boundary, we have to replace this here by what we derived here. Then we have a complete discretization for the whole domain. So we can just summarize that. Approximation A that we derive, and we use also 8 for J for the last cell Nj with the approximation B that we have here. All this will give us Nj equations. That constitutes these equations, or constitute, let's see, a system of ODEs, that is, ordinary differential equations. Expressed in a way that we can easily discuss it, the solution mathematically. And that would be then the following. We introduce now T as a vector containing all the approximations of the temperatures in each cell. And on the right-hand side, we have what we have here also printed on the right-hand side. And that depends on T, the time, with the boundary conditions, and the vector T of the unknown approximations of the cell averages. So, and that is the following. The T is here then the vector containing the approximation of the temperature in cell 1, cell 2, and so on, until the temperature in cell Nj. So these are the unknowns that we have to determine. And the right-hand side, the R of the general would be T. If we would not have time-dependent boundary conditions, we would just have a dependence on the unknowns. The time comes only through the boundaries. So if the boundary conditions we have constant temperatures, then this dependence on time will be gone. And that will be then a vector that contains R1 and so on to R and J. Now the R's are then given by what we have here. Let's write that down. So the R's are still to be determined, that we do now. So we have the R's are then with the following, that we call it 10A for first the R1. The R1, let's see. If we look at this equation here, what we have here is are expressions of dt dt. So for the cell 1, we can use this approximation. Then it will be delta x1, this will be t1, this will be alpha 1 plus 1/2, t2 minus t1, and so on. But here we will use our approximation A. So what will be that? If we want to have this expression, we divide by the delta x1. So that will be, therefore we will divide something. What we get here then is then the alpha 1 plus 1/2. Here we have t2 minus t1, x2 minus x1. So we have this formula for j equal to 1. Minus, now we use the approximation A that we had discussed before. That was alpha A. And here comes the boundary condition, t1 minus ta. So if ta is time dependent, we get this time dependency. If it's not, then we don't have it. Divided by the distance between the midpoint of the first cell and the x-coordinate of the left boundary. And that is all to be divided by delta x1. Because this guy, we want to have this form, so we divide by that. So that is then easy. Now the other stuff, what we have to do is then for the interior cells, we can use this expression. We simply have to divide, then to get the right hand side, we have to divide this by delta xj. So now I make life a little easier for me. And that will be then the 10b. That will be then rj. And that will be then divided by delta xj. Divided by delta xj. So that is then the approximation that we need for cells 2 to nj minus 1. We can use that. So then we have simply the last one left, that is in the last cell. We use still similar expression, but then we have j equal to nj. So that is then the 10c. R and j is equal to, we make here a similar thing as we did before. However, here we have now to use b. Remember, the right boundary we cannot use this formula because we don't have a right either to cell nj. So we have the alpha b, and here we have the tb minus the tnj divided by xb minus xnj. Minus, and here we can use what we usually use simply for j equal to nj. That is then nj minus 1/2 times tnj minus tnj minus 1 divided by xnj minus the xnj divide by the distance, by the length of the last cell, which is then delta x nj. So that will be then the formula for nj. This was the formula for 1. So then we have our formula complete to describe the r's. And again, time dependency might come in to the right boundary, Tb, because that might depend on time. In our case, it does not. So in our case, neither the left boundary temperature Ta nor the right one, Tb, depend on time. In that case, this dependency on time will be gone. So we'll simply have the right-hand side will simply depend on the temperature, the unknown itself, not on time. Okay, so then you see the general formulation, and what we shall do after the break is to look at the special case when we have an equidistant grid, when the distances between the grid points are the same. That will be also what we will do in exercise 2. But we have here the general formulation, so you can have any distribution. So that is, again, a strength of the finite volume method, that you don't need to do anything, you just can do these approximations. However, there is a but. It is always useful to have a smooth variation of the size of the control volume. So don't let the size be, say, you have small sizes and suddenly you have big sizes. Then at these jumps, the accuracy or even the consistency of the method might fail. So therefore, if you do a variation in the spacing of the control volumes, then vary it smoothly. That is the advice. Okay, so then we take a 15 minutes break.